All right, let's get underway. Good morning. Welcome to sunny Seattle, Washington. I'm Rick Fienberg, the AAS press officer, and I'm delighted to see a full house here for the first of 8 briefings at this 225th meeting of the American Astronomical Society in Seattle. I have 2 deputy press officers who are working with me at the meeting. They're both here in the room. Inga Heyer is in the back. She's monitoring our webcast. And Larry Marshall over here on your right will be helping with the Q&A. Please, if you have a cell phone or a beeper or anything else like that, please make sure it's silenced. So if this is your first AAS press conference, you'll appreciate knowing how we do it here. I'll give a brief introduction to the subject this morning, and then I'll introduce our speakers. They will speak in turn, and we will hold questions until the very end. We do this to ensure that questions for the first couple of speakers don't end up robbing the last couple of speakers of all their time. And if you're tuned into the webcast, please log in and you can ask questions via text chat, and then Inga will relay those questions to me or to the panelists at the end of the briefing. All right, so this morning's briefing is about exoplanets. Exoplanets have supplanted black holes as the most popular press conference topic. We now have multiple exoplanet briefings. This is quite a change from when I was a graduate student or even when I used to work at Sky and Telescope. Exoplanets didn't exist except in people's imagination. And now, it's the subject of a very large number of science sessions at our meetings. So today we're going to hear 3 results presented by 3 scientists who are all from the Harvard-Smithsonian Center for Astrophysics, and by saying that once, I've saved myself 5 minutes. Now, I've been very sly in adding a commentator from Yale, and if you know anything about Harvard and Yale, you know that that really is very sly and potentially dangerous. So our speakers this morning, one more announcement. I just wanted to make sure that all of our press registrants are aware of the AIP press reception that's tomorrow evening at 5:30 next door between this room and the press room, celebrating the AIP Science Communication Award winners, 2 of whom are here at the meeting. All right, so this morning's briefings are from Søren Meibom, who's going to be talking about the Kepler cluster study toward the ages of stars and their planets. He'll be followed by Courtney, who will be talking about a recipe for Earth-like planets. And she'll be followed by Schaefer, talking about the persistence of oceans on Earth-like planets. And then our commentary will be provided by Debra Fischer of Yale, who has been in this business as long as anybody and will give us some perspective on where today's results fit into the bigger picture. And with that, I will turn it over to Søren, and I will even try to bring up Søren's presentation before I sit down.
Thank you, Rick. Good morning. As you know, NASA's Kepler mission has been tremendously successful in helping us understand the frequency and the diversity of planets and planetary systems beyond our own. Today, I will tell you about the latest results from the Kepler cluster study. As part of the original Kepler mission, a main goal of the Kepler cluster study was to build a clock for the stars. That is to say, to make measurements with Kepler to help us develop a method to determine the precise ages of cool stars. So what are cool stars? And why is it important to know their ages? A cool star is a star similar to our sun, or smaller. They're most numerous throughout the solar neighborhood and the galaxy. And they also live very long lives. So they act as lampposts, lighting up even the oldest parts of our galaxy. So numerous and luminous, young and old, astronomers use cool stars to study the universe from its early days till recent times. So now I have told you about the value of cool stars. Why do we want to know their ages? Well, just as organisms here on Earth change and evolve with time, so do stars and planets. And to understand this evolution, we need to establish a sequence of events. Here on Earth, for example, in order for us to understand the evolution of our own species over millions of years, we had to develop methods to date the fossil bones of our ancestors. But in space, the formation and evolution of stars and planets, clusters of stars and galaxies, takes place over hundreds of millions of years, even billions of years. And knowing the ages of the stars that make up these systems is as important to our understanding of astronomical phenomena as it has been to us to understand the human evolution, to know to be able to date the bones of our ancestors. So now you know why it's important to know their ages. So the next thing I'm going to tell you is determining the age of a cool star is a very difficult task. And the reason is this. As this diagram illustrates, the mass and the size of a cool star remains almost constant throughout its life, as well as its most easily observable properties, such as brightness and temperature. And to drive this point home, I usually ask you to imagine for a moment that the same was true for human beings. Let's imagine that we were born as small babies, but by our first birthday, we look like an adult. And we stayed looking the same through our 20s and 40s and 60s, even 80s, until we suddenly appear old. If that was true for humans, we wouldn't be able to look at each other and tell each other's ages. We would have to find something else about us that would change steadily and visibly as we grow older. And that is our challenge for cool stars. To find something about cool stars that change steadily with time and that we can observe. Luckily, there is one such property for a cool star. Its spin rate. A cool star's spin is very fast when it's young, but just like a top on a table, it gets slower and slower as the star grows older. So we can use the spin rate of a cool star as a clock, and we refer to this method as gyrochronology. So the idea of this clock is really simple. We want to make measurements of the spin rates of cool stars for which we already know the ages. And we want to then establish a relationship between spin and age for cool stars in general. Because if we can do that, then we can take any cool star in the sky and measure its spin period and use this relationship to determine its age. Now, why do we need NASA's Kepler mission to do this seemingly simple task? Let me answer that by showing you how much of this clock we had built before Kepler and the Kepler cluster study. We knew spins and ages for cool stars younger than about 600 million years. And you may ask me, how come we knew the ages of those stars? And this is where the word cluster in the Kepler cluster study becomes relevant. And today, the only thing I want you to remember about star clusters is that we can determine their ages, and thus the ages of their stars, well, simply by plotting their colors and their brightnesses and examining the pattern that we see. So the three rapidly spinning stars in the lower left part of this diagram represent measurements of cool star spin period in young open clusters. But beyond that, the only good information we have about the spin-age relationship for cool stars is from our own cool star, the Sun, at 4.6 billion years, leaving us with a 4 billion year gap. And that is where Kepler comes into the picture. See, the way we determine the spin period of a cool star is by measuring periodic changes in its brightness as dark spots on its surface cross its face and disappears on the backside again. That's illustrated by the star and the graph over on the left side here. Young stars spin really quickly, and they have large and big spots. So their brightness fluctuations are large and of short duration and relatively easy to measure. But as stars grow older, as you can see in the center and the right panel, they have fewer and smaller spots, and so the brightness fluctuations become smaller and of longer duration, and thus much harder to measure. And so for clusters older than about 600 million years, we have not been able to measure the spin periods for cool stars for decades. And so the construction of the cool star clock was on hold. But with Kepler, we've been able to break this deadlock because Kepler provides us with very precise measurements of the stellar brightness over years. And so, in 2011, the Kepler cluster study provided us with the first measurements of spin periods for cool stars in a 1 billion-year-old cluster, NGC 6811. And today, I announce that we have now bridged this gap to the Sun by measuring the spin periods of cool stars in the 2.5 billion-year-old cluster, NGC 6819. And these new measurements allow us to trace the spin history of our Sun from its current 26-day period to 18 days at about 2.5 billion years, to 11 days at 1 billion years, and so on. But we're not restricted to stars just like our Sun, because our measurements establish the spin-age relationship for stars that are both larger and more massive than the Sun, and stars that are smaller and less massive. So as you can see, we have made important progress in terms of measuring the spin history of cool stars. And by doing so, we have taken steps toward constructing this clock that will be able to provide us with their ages. So let me end by emphasizing the value of this clock to our study of planets and planetary systems beyond our own. As Søren and Courtney will tell you in a few minutes, the field of extrasolar planets is branching into the studies of formation and evolution of planetary systems and of planets themselves and their atmospheres. And for all of these areas of study, knowing the ages of the planets is essential. Fortunately, a star and its planets form together at the same time, and so they share the same age. So if we can determine the age of a star, we also have the ages of its planets. And so as we find more and more rocky planets the size of Earth at distances from their stars so that life might have had a chance to evolve, an essential question becomes, how old are these planets? Because we know from studying our old planet that it went from being lifeless at 1 billion years through primitive life at 3 billion years to a planet teeming with complex intelligent life at 4.6 billion years. And we may have to learn interesting things about our own planet, the future of our own planet, the fate of our own planet, by studying solar-like, Earth-like planets around cool stars older than the Sun. So I just want to end by thanking my collaborators and the funding agencies supporting this work. Thank you.
Good morning, everyone. I'm Courtney Dressing. I'm also from the Harvard-Smithsonian Center for Astrophysics. I'm sure many of you have noticed that there are many, many cooking shows on TV right now. The foodie revolution has expanded. Everyone wants to learn all of the latest recipes, go try out the best new dishes at nearby restaurants. And today, I'm going to tell you something special. I'm going to give you the recipe to build a rocky planet. This work was made possible with the HARPS-North collaboration. As many of you probably know, most planets orbiting stars outside our solar system are completely unlike anything in our solar system. Here I have a plot showing you on the left side the sizes of planets, and on the bottom, the length of a year on those planets. I'm going to put up a diagram showing where most of these planets fall. They're within this yellow box, which is planets that are between 1 and 4 Earth radii. These planets are unlike the planets in our solar system. They're bigger than the Earth, smaller than Neptune. What are they made out of? We can't tell by looking at the planets in our solar system. We need to use telescopes to measure the sizes and masses of planets like these orbiting other stars. To do that, we have wonderful radius measurements from the Kepler mission. From the ground, we're using the Italian National Telescope Galileo. You can see a picture of the telescope here. We're using the HARPS-North spectrograph, pictured on the bottom right, in order to conduct an intensive campaign measuring the masses of small planets orbiting small stars and stars like the Sun. This is an international effort, and so far we've contributed a handful of very precisely measured planets to our understanding of the properties of planets between Earth size and Neptune size. We want to know what kind of recipe we need to follow in order to build these planets. Here are a selection of recipes we might imagine following. This is a plot showing on the left side sizes of planets compared to the Earth versus the mass of the planet on the bottom. All of the colored lines show a different example of a recipe. The blue line is the recipe you would follow to make a planet entirely of water. Those planets are pretty big and fluffy compared to the planet you would get if you followed the recipe in the white line, which is a rocky planet. That rocky planet would end up close to where the Earth and Venus are, there on the bottom left of the diagram. You could try to follow a recipe shown in yellow, or shown in red actually, for an all-iron planet, but I wouldn't recommend doing that because we don't think such planets exist in reality. We don't expect to find any planets in this gray region in the lower right, just because of the starting materials we have. Now that I've shown you our selection of recipes, where do the actual planets fall? Prior to our campaign with HARPS North, we had two objects on this diagram with masses and radii measured to precisions above 20%. And the reason why I'm only going to show you planets with precision of 20% or better is that some of these models are very similar, and we want to be able to figure out which of these models best describe the planet. So let's look at the planets we had before. They were Corot 7b, shown in purple. That's the smallest planet from the Corot mission, and Kepler 36b, shown in pink. That planet has a mass and a radius measured from the Kepler data using a technique called transit timing variations. From HARPS North, we have a mass measurement for the planet Kepler 78b. And the HiRes team in California has also confirmed our measurement of the mass of Kepler 78b. We also had a paper earlier this year led by Xavier Dumusc on the mass of Kepler 10b. Right now, today, I'm announcing the planet Kepler 93b. You'll notice that the size of this planet is constrained very tightly because of astroseismology measurements of the host star made by Sarah Ballard and her collaborators. Looking at these planets, you can see that they fall between the white line of all rock planets and the red line of 50-50 rock-iron planets. That suggests that they might all be made from a common recipe. In fact, we do find a recipe that fits all those planets. It's this blue line. That's the recipe you follow to build an Earth. If you notice, we only fit this line to the 5 small exoplanets pictured, but it goes right past the Earth and Venus, showing that these planets have an Earth-like composition. What happens for the larger planets? Can we build them with the same recipe? Turns out no, you can't double the recipe that much. It doesn't work. The large planets really require some lighter material. They require fluffy things like gases and ices. They're not explained by the blue line. We now know, thanks to our intensive observing campaign with HARPS North and wonderful radii from Kepler and Corot, that the compositions of planets between 1 and 6 Earth masses are more Earth-like. If we were to cut them open, we'd see something that looks more like the picture on the left. For the larger planets, things 6 Earth masses or higher, we'd see something like Neptune, or maybe we'd see a rocky ball covered with big, fluffy envelopes of hydrogen and helium gas. Today, if you're not too worn out from all the holiday baking, when you get back home, I'd encourage you to check out a new recipe for forming rocky planets. You'll need the following ingredients, so go to your cupboards, please. I want you to put together a cup of magnesium, a cup of silicon, 2 cups of iron, 2 cups of oxygen, mix well, but don't overmix. That's always a problem when baking. Then go to your spice cabinet, put together a ½ teaspoon aluminum, ½ teaspoon calcium, ¼ teaspoon sulfur. Then you're going to need to bake this, and you're going to need to be very patient. You need to bake this for a couple million years until you start to see a thin, light brown crust form on the surface of the planet. Take it out, be careful not to burn yourself. Then go to the cupboard, get some water, and just season to taste with a dash of water. And Laura Schaefer will tell you about how much water you should add to this planet. Finally, you're going to need to wait a longer time again, just like Søren told us. And if you check back in a couple billion years, maybe you'll see some intelligent life on your planet. 2 things to keep in mind when making this recipe. The first is that this should work for things between 1 and 1.6 Earth radii, but don't double it too much because it doesn't work for things 6 Earth masses or higher. If you run into any problems while you're baking, please give me a call. Thank you very much. And up next, we have Laura Schaefer on the persistence of oceans on small planets.
Thank you, Courtney. As Courtney said, I'm Laura Schaefer, and I'm here to talk to you about the fate of oceans on Earth-like planets. So I thought I'd start off with a pretty typical astronomical image right here. No, just kidding. We'll start with the next one. This is a pretty typical photograph of the Earth from space. So when we look at this picture, what's our overwhelming impression of it? Carl Sagan called it the pale blue dot, and indeed it's the color blue that strikes us most about our planet that makes it the most distinct amongst the solar system planets. Now, when astronomers like Courtney are looking for planets in the habitable zone, this is what they're looking for, a rocky planet that has some water on its surface. Now, what happens if we change the size of the planets? Courtney was just telling us about all of these planets in 1 to 5 Earth mass range that have the same composition as the Earth, but do they still have an ocean? And that's what I want to look at here. Now, these models of habitable zones are pretty sophisticated, but they really deal only with the surface environment, with the atmosphere, which controls the surface temperature. And this is a photograph of the Earth's atmosphere from the International Space Station. But the Earth's atmosphere really only accounts for less than 0.1% of the Earth's total mass. And if we zoom out to a diagram of the whole Earth, it actually vanishes to less than the thickness of a line. So it's not really the only thing that determines if the water that a planet has will be on its surface. Now we know that on the Earth's surface today we have 1 ocean mass of water, but geochemical studies tell us that there's anywhere from 1 to 10 times as much water in the Earth's interior, in its mantle. Now what happens if all of that water is on the surface? Well, we don't have any exposed continental surfaces, and life as we know it couldn't exist. Imagine Kevin Costner's Waterworld. I don't know, maybe not. Now, on the Earth, we know that water is exchanged between the surface and the interior through plate tectonics. Minerals on the ocean floor trap water in their chemical structure, as shown in the small boxes at the bottom of this figure. Now, those minerals are transported into the Earth's mantle when the ocean crust sinks beneath neighboring crusts in a process we call subduction. Now, that trapped water is cycled through the mantle, and it can be brought back to the surface when those rocks melt and cause volcanic eruptions. And we refer to this exchange between the surface and the interior as the deep water cycle. Now, plate tectonics, and therefore the deep water cycle, they're both driven by cooling of the mantle. The mantle is mostly heated by decay of radioactive isotopes, and since their abundances are constantly diminishing, we know that the rate of the cooling, and therefore the rate of the deep water cycle, also has to change with time. So we can't assume the abundance of water at the surface is a constant. In order to model the deep water cycle on Earth-like planets, I have taken a well-known model for the Earth, which calculates both the change in temperature and the rate of water exchange with time using pretty simple parameterizations. Those parameters include the effect that temperature has on the rates of subduction and volcanism, as well as the effect that water has on the material properties of the mantle. Now, when you add water into rocks, it makes them less viscous, so they flow more quickly, like if you take cold honey and you warm it up. Now, pressure also has a similar reverse effect on the material properties of the mantle as well. If you increase the pressure, rocks become less viscous. So there's a competing mechanism here, where if we have a larger planet, we're going to have higher viscosities. So we expect some influence of planet mass on these models. Now, what I've done is to take planets between half an Earth mass and 5 Earth masses with the same mixtures of water to rock and metal as on the Earth. So we know from Kepler mission that planets in this size range are common, and from Courtney's work that this composition is also common. And we started our models from the time of the planet's formation, and we allow the planets to evolve with time. And we're tracking both the internal temperature of the planet and the way that the water on the surface and in the mantle are being exchanged. Now, what we found was that for small planets of about 1 Earth mass or smaller, they outgas oceans very quickly, so they have a very early and very deep ocean. But as the planets get larger, the outgassing is a little bit delayed, and the larger the planet is, the larger that delay is. So for 5 Earth mass planets, we found that their ocean formation could be delayed up to 1 billion years. This is because those planets are initially not hot enough to allow outgassing, and radioactive decay eventually warms the planet's interior up to the point where it does melt and it does begin forming oceans. Now, the early activity on the small planets, unfortunately, also makes them die out faster. So they release all their heat to the surface, but as they do that, the water that was originally on the surface becomes trapped into the interior. Planets of about the Earth size and about 2 Earth masses lose a little bit of water to their interiors over time, but they don't lose all of it. So their oceans are going to be a little shallower by the end of their lifetime, but they'll still be there. And the larger planets, the 5 Earth mass planets, their oceans only continue to grow through time. So they start out fairly thin, and they just get deeper with time. Now, the presence of liquid water on a planet is agreed by most biologists to be a necessary ingredient for the origins of life. So these models are important because they show that those oceans aren't static. A planet with an ocean could lose it to its interior despite having a protective atmosphere, whereas larger planets might have this delay in ocean formation. So we know that complex life on the Earth took many billions of years to develop, so that means that complex life on these larger planets might also be delayed. So therefore, knowing the age of a planet is just as important to determining its probability for having life as knowing its orbital properties. So someday, with the help of astronomers like Søren, who are measuring ages, and Courtney, who's measuring the composition and characterizing these planets, maybe we can find a planet that's just right. So here's a brief summary, and thank you.
Harvard versus Yale. We're going to have to, hopefully it's not going to be like the football game this year, but. Okay, so I've been asked to sort of give a 20-year perspective. The idea is that 20 years ago, we found the first planet orbiting a sun-like star, 51 Peg. Michel Mayor and Didier Queloz discovered this exactly 20 years ago. This is incredible because just before that time, I remember astronomers feeling very worried. We'd been looking, or scientists had been looking for a long time for exoplanets for decades and hadn't found any. And we really had to step back and say, you know, we have to entertain the possibility that maybe the Star Trek picture of the universe isn't right. Maybe there are no other planets around other stars, or they're there rarely. Okay, and that was a perspective that sort of filled me with despair, I have to say. I imagined that, you know, here's the universe twinkling with the light of billions of stars, and yet there may not be any planets around those other stars. And the reason that that was interesting and profound and moving to me is because the implication then would be that there's no life anywhere else. And how can you have a whole universe filled with stars and no planets and no life anywhere else? That was incredible. And so I think we have to acknowledge right now what an incredible change we've seen in 20 years, right? Especially with the Kepler telescope and the results that now tell us that almost every star has a planetary system. It's absolutely incredible. And I think we should also take a step back and remember that everything that's been discussed today, talking about stars and the globular clusters and finding this planet around a Kepler star and thinking about the oceans of water, these folks are talking about something that is the invisible universe, okay? To most humans who occupy this planet, you can't look up in the sky and see any of these things. So it requires the incredible telescopes and technology that we've developed to even know that the host stars exist. And now, around a star that is, you know, hundreds or millions of light years away, we're talking about a planet. We can barely see the star, right, except for with powerful telescopes. And we certainly don't see the planet. And yet we're able to talk about the mass of the planet, the radius of the planet, the bulk composition of the planet, right? We can draw a diagram where we do an orange, you know, or grapefruit sort of slicing through the core and see the core of the planet and really talk about this in a serious scientific dialogue. So this is incredible, right? Incredibly moving. We now know that Earth-like planets are very common. And so we also should think about, what do these discoveries mean for people here on Earth, for Earthlings? Well, they give us a better understanding of the solar system, how we formed. We see these odd things in our solar system that suggested even in the 1980s that Neptune and Uranus probably formed in between Jupiter and Saturn and then were scattered out. But there was no real motivation for this idea until hundreds of exoplanets were discovered, and we see that planets migrate and scatter and move around in planetary systems commonly. That gave us new eyes, a new way to look at our own solar system and to understand our own solar system. The other thing that's happened in the past 20 years, that I've been looking for exoplanets and finding them, is that the work that's been done by biochemists is really impressive. I've taught some form of astrobiology for 10 years now, and our understanding of the origin of life on this planet has made some incredible progress, some incredible advances. But we're still at a point where we're stuck with one example, right, of how life formed on Earth. And so there probably won't be a unique way to answer the question of whether or not there's, how the origin of life started here. Unless we find other planets. We now know the universe is teeming with planets. Okay, the next step is to figure out if the universe is teeming with life, if those planets have life. If, as the biochemistry that's being done here on Earth suggests, that life is the natural outcome of equilibrium system chemistry on a planet like the Earth, the same mass, the same radius, the same temperature, same pressure composition, right? If we find other worlds that are similar, will life be a natural outcome of biochemistry on those planets, right? So I think that's where we're going. And to have come from the last 20 years, 0 planets, to where we are now, billions of planets in our solar system, and to think about, the fact that these young researchers are looking for, trying to better understand the composition of planets and whether or not they have water, right? The habitability factors that come at the very heart of why we're looking for exoplanets is really amazing and impressive work. If you were here in the last, yesterday or the day before, you've heard about NASA's plans for the future. And I would say that they are as exciting and as visionary as ever. And the international participation is growing and incredibly vibrant. This is an international collaboration, and it's really exciting to see the best in the world come together. So I think that for the future now, the question will be, where are the habitable planets around nearby stars? How do we find them? Are they alive? And then I think the third question is, how do we get there? Right? So that's the question that NASA, I think, will address in the next sort of long-term vision, 20, 30, 40, 50 years. But still, that's not so long. I was just thinking the other night that when I was in first grade, I remember hearing that John Kennedy had been shot, right? And that they were going to sequester the records for 50 years. And it just seemed overwhelming. We'll never know the answer, right? But in those kinds of timescales of human lifetimes, things change. And the information comes back and we see a whole new perspective. So I just congratulate my colleagues on these incredible discoveries and thank them for their work.
All right, thank you all very much. We're going to do the Q&A now, and I want to remind everybody to wait for a microphone so that the people on the webcast can hear your question, and also to please identify yourself and tell us who you're writing for. We'll start here in the room, and then we'll see if there are any questions online. So we'll start down here with Carolyn, and then we'll go to Alex, and there was one in the back too, I think, but start with Carolyn.
I'm Carolyn Peterson from Loch Ness Productions. One of the things that Rick said actually was, it used to be black holes were the big stories, and now it's planets. And I remember when I was in first grade, black holes were theoretical. So now we're... Anyway, in recent months and weeks, I've been reading about the water in the mantle and that sort of hypothesis about what's happening with that water. And the most recent discussions have been, where did that water come from? Does your recipe care where the water comes from in the solar system? Okay.
No, we don't really care where the water comes from. We think that, however it was delivered, that water got transported into the mantle fairly quickly. Water's we probably had what we called a magma ocean in the early stages of planet formation. And water is pretty soluble in the magma ocean, so it would not have been hard to get the water into the mantle.
Alex Witzy with Nature for Courtney. Can you talk a little bit about why the recipes are different for small versus larger planets?
We think it ties back into planet formation, that as you start to put things together to build a planet, once you reach a certain mass, it's much easier to acquire lighter materials. The other issue might be is that all of these small planets we've studied so far are very close to their stars. So if they had big fluffy envelopes to begin with, they might have been able to lose some of those. So in the future, as we find more planets with TESS and with K2, it would be really great to study planets both close to their stars and farther away to see if the same relation holds for planets that are more distant.
The questions here in the room? Okay, we'll take Govert and Jeff. Govert?
Govert Schilling, freelance from the Netherlands. Question for Laura. I seem to remember that Venus doesn't have too much plate tectonics. How can you be so sure that your super Earths have these geological cycles like plate tectonics? Can there be any planets that are just solid crust?
Right, that's possible. So Venus, we think, started out with a very similar amount of water as the Earth did, and it lost it because its surface temperature is much hotter than the Earth's. We did in these models assume that these planets had plate tectonics, and you can argue about whether that's a valid assumption. But we think that one of the reasons that the Earth does have plate tectonics is because we do still have water. So there are theories that water is essential for plate tectonics to occur. So the fact that we didn't lose our water is important. So our models do then assume that these planets keep their water and that they do have plate tectonics, yes.
Okay, we'll take Jeff too.
All right.
Go ahead.
Jeff Faust, Space Review. For Courtney Dressing, can you give an idea of what that transition is like around 6 Earth masses from rocky to icy? Is it sudden? Is there a more gradual transition, either from the data you have or from planet model theory?
That's a fantastic question, and it's one that many people are eagerly trying to answer. There was a paper by Leslie Rogers where she investigated whether you could have a sharp transition or a gradual transition. She found slight evidence in favor of a gradual transition, but we don't yet have enough data to say for sure. And as we get more planets with more measured masses and radii and put them on that diagram, we'll be able to tell you.
I actually have a question for Søren, because Courtney mentioned that the planets that you wanted to plot on your graph of recipes, you wanted to limit those to the ones that were known to better than 20%. And Søren, you talked about determining stellar ages, and I'm curious how accurate this method is that you've got. Are you in a 20% or better type of range, or is it still more uncertain than that?
Yeah, I mean, excuse me. That's the exciting thing about this new larger sample of periods we've been able to measure in this older cluster is that we actually have a sample where we can get a better estimate of the precision of ages. And we estimate in the paper that is out today around 10%. If you can measure the spin period of a star well, like we can with Kepler, then you can get its age to in the ballpark of 10%.
That's great, especially when you consider that for decades we were trying to get the Hubble parameter to better than 50%. So 10%, it's impressive.
And it should be compared to alternative methods where it's easily 100% for the kind of stars we're talking about.
Okay. Any more questions here in the room? Larry?
Yes, I have one, which, again, for Søren. You have all of these period measurements for these stars in these two clusters in the Kepler sample. As time goes on, you're also going to get spectra of the stars, and I wonder, maybe it's premature, whether you can say anything about whether there's any system in the inclinations of the stars in these clusters.
If there's any...
because you get period and you get V sin I. Can you say anything about the sin I?
Whether there's any trends in terms of the orientation of the stars in the cluster.
Right.
I have not yet looked at that, but other people have looked at it in other clusters where both photometric rotation periods have been measured, spin periods, and the V sin I. And in those studies, it's been consistent with random orientation if that was your question.
Yes.
So I haven't done it in these clusters, but in the other clusters that have been observed, it's been consistent with a random orientation.
Okay, we have one down here in the front, Dan. Inge, do we have any coming in online? We do. Okay, so we'll go online next.
Hi, Dan Cleary from Science Magazine. For Søren, how do you, these brightness variations that you see, how do you know they're not caused by a close-in exoplanet?
So that's a very good question. When the signal is actually quite different. The spots are sitting on the surface of the star, so to speak, and so as they come onto the face of the star and transits in the star in that sense and disappears again, you get a sinusoidal kind of signal, like a wave pattern, whereas a transiting planet that is in a distance from a star will transit the star just in a few hours or so, and so you get this classic dip. So the signal is very different between the two, but it's a good question.
Okay, we'll take a few questions from the webcast audience.
Okay, the first question from the web is from Seth Borenstein of the Associated Press. For Courtney, can you explain how you came up with those proportions? Does it mean no other proportions would create a rocky planet? And can you give us the size, location, and other details of Kepler 93b you just announced?
So I'll start with the last part first. Kepler 93b is 1.5 Earth radii, and it's 4 Earth masses, and it has a density of 6.9 grams per cc. And it's in the Kepler field, so it's between Cygnus and Lyra in the night sky.
That density is comparable to Mercury, right?
Yes, but the difference is that Kepler 93b is bigger, so you need to account for the fact that when you build a planet bigger, you need to have a higher density in order to have an Earth-like composition. The other question was, how do we actually get that precise ratio, and could other ratios also work? We find that ratio is preferred for the composition of the planets, but you could have a bit of scatter on either side. But we see it's a very tight relation, and the tightness of that relation is quite exciting to us.
Okay, thank you. The second question comes from Salvador Nogueira, a science writer for Folha in Brazil. The question is for Laura. I wonder what are the implications of this work for M-dwarf planets. A recent study has called into question the survival of surface water on planets around M-dwarfs in the habitable zone because during the pre-main sequence phase, the excessive brightness would boil all the water away. Does your analysis improve on the expectations of finding oceans on M-dwarf planets?
So our models are actually agnostic to the planet's orbital location or the star type. So we assume a constant temperature equal to the surface temperature equal to the Earth's. So the next step for these models would be to link this to an atmospheric loss model, because you're right, hydrogen can escape from atmospheres. It's less likely for the 5 Earth mass planets than it is for the smaller ones, like Mars-sized. But certainly that's something we need to incorporate into future models. So right now we can't really say anything specific about M-dwarf planets.
Thank you. The next question is from Tracy Watson of USA Today, also for Laura. How big a water body do you mean by ocean? Something that covers the planet's whole surface, or perhaps smaller?
So one ocean mass means the amount of water that we have at the surface today. So that incorporates all of our present-day oceans. Now, the mass of the water on the surfaces of these planets does vary with time, and we can estimate its depth using models for continental thicknesses and so forth. Typically, it's less than the current amount of water at the Earth's surface today. So it would not be full ocean coverage. So that's particularly true for the large planets, the 5 Earth mass. So if you have the same amount of water at the surface of a 5 Earth mass planet, it's not going to cover as much surface area. So those oceans will be much patchier than on the smaller planets.
Okay, thank you. That's it from the web.
Okay, any other questions here in the room? Yep, one here in the back. Please remember to identify yourself.
Yeah, Mark Harris here. I'm a freelance. Question for Søren. Will your technique ever be able to date stars as old as the sun? I mean, or do we just get to the point where the sunspots are too small and too slow to use that technique?
So 2.5 billion years is our current record. And with K2, the current version of Kepler, the successor to the original Kepler mission, we are going to try to measure rotation periods in a star cluster that is much closer in age to the Sun, around 4 billion years. Time will show whether we can do that or not. But I think it's a bright future in that sense. We have many other missions coming along. We have the K2, first of all. There'll be tests. There'll be important ground-based missions, the LSST. And so I think it's promising that we will get more and more long baseline photometric brightness measurements of stars all over the sky, not just in a small field, but all over the sky, especially for more nearby old stars. So while we haven't yet done it, I think it's very likely that we will be able to measure the spin periods of many, many stars across the sky that are as old as our Sun, or maybe even older. But it is very challenging because, as I said, the star spots become fewer and smaller, and they don't live as long. So you need high quality data to do it, but we will get that in the future, I believe.
Okay, one more in the back.
Okay, yeah, a follow-up question from Seth Bornstein of the Associated Press. For Debra, does the recipe given today make sense? Why or why not? Or is the sample size too small to make this leap?
I love the recipe. This is incredible. Yeah, so there's, as Courtney said, there's some degeneracy in the models. I think Zhang probably worked on these as well. And depending on the complexity and the number of layers that you assume, there's a little bit more play. But yeah, they make sense. And the fact that they lie just empirically along this line in the mass radius diagram with a bulk density, similar to the Earth, I think is extremely suggestive. And then you see a rapid departure when you move away from that. So there can be a little bit of play, I think, probably in the chemistry of the planets, but that they are so Earth-like is really remarkable. There aren't a lot of things that are falling very far off the line.
Thank you.
Did you have another question here? No? Any other questions? All right. Well, then we'll call it a wrap. I want to thank our speakers again, Søren Meibom, Courtney Dressing, Laura Schaefer, and Debra Fischer. And I want to also thank you for coming this morning. It's very gratifying to see a full house. We don't usually have standing room only at our briefings, but maybe we'll start a trend. Thanks also to the webcast audience. We have 2 briefings a day, and the next briefing today is at 2:15 Pacific time, and it's themed around the Milky Way and the local group of galaxies, so I hope you come back for that. And then, of course, we have 2 more briefings each day all the way through Thursday. Final reminder, we do have an AIP press reception tomorrow evening at 5:30, right before the press dinner, and that'll be occurring in the room next door here between the press office and this room. So thanks again, and with that, we'll call it a wrap. Thank you.